Okay, so now that we've talked about SN2 reactions, let's talk a little bit about the other possibility. And what we said with SN2 reactions was that tertiary halides, like the one shown here, tertiary butyl bromide, does not undergo SN2. Now, how do we actually know that? Well, let's say we designed a kinetics experiment to look at this reaction. So what I'm going to do is I'm going to take and I'm going to react my nucleophile with the tertiary halide. So I'm going to move it off the arrow and move it over here. And let's say that we design an experiment, kinetics experiment, to determine the kinetic rate order. So in experiment 1, again, we would use for our concentration of the nucleophile and our concentration of the alkyl halide, let's say we use 1 molar each. And the corresponding rate that we got was, let's say, 1 of whatever units. So that would be experiment 1. Then in experiment 2, we do the same thing that we did before, which is we double the concentration of the nucleophile, keep the concentration of the alkyl halide the same, and what we measure is the rate is still 1. So we might go back and reproduce that experiment. We might go to experiment 3 and say, let's go to 3 molar, and we still get a rate of 1. So then we'd say, well, okay, let's keep the concentration of the nucleophile 1 molar and let's go to 2 molar for the alkyl halide, and the rate becomes 2. Then maybe we say, okay, let's go to 3 molar nucleophile, and we would get the rate to go to 3. So this is, if this happened, you would immediately look at this and go, well, wait, this molecule's not in the same, it's not reacting by the same mechanism because it doesn't have the same kinetics. And you'd be correct. It's not the same kinetics. And it's therefore not going to have the same mechanism. So what is the overall rate equation then? The overall rate equation would equal the rate constant times the concentration of the nucleophile now to the 0 power times the concentration of the alkyl halide to the first power. Now any number to the 0 power is equal to 1. So really the rate equation for this reaction was determined to be the rate constant times the concentration of the alkyl halide. It doesn't matter what the concentration of the nucleophile is. And that's interesting. Now what we have is not an overall bimolecular reaction. We have a unimolecular reaction because the overall rate order is 1. And so the reason we use kinetics, the importance of kinetics, is it helps us elucidate mechanisms. And when you have a change in kinetics, you typically have a change in mechanism. So this is telling me, hey, a tertiary halide does not undergo the same mechanism as a primary halide or a secondary halide with a strong nucleophile. And so then the question is, well, what kind of mechanism do we propose that accounts for this unimolecular reaction? And so now let's take a look at what is the mechanism, and it'll become clear why that's the case. So what's been proposed for the mechanism of SN1, and nobody's disputed it or disproven it yet, is that we take the alkyl halide and we're going to replace it with the nucleophile, but in the first step of the mechanism, so now it's not a one-step mechanism concerted, it's going to be a multiple-step reaction. So in the first step, what I'm going to do is I'm going to break the carbon-bromine bond, and I'm going to form a carbon with a positive charge, a positive 1 formal charge, and then the leaving group as the bromide. Now, this species, this carbon has 6 valence electrons, but it has an overall formal charge of positive 1. And it's called a carbocation. It's sometimes also called a carbonium ion. So we have the carbocation, and that is our first step in the reaction, is to form the carbocation. Now, what happens then? What happens in the next step of the mechanism is that the nucleophile will come in and take its pair of electrons, and it will donate it to the carbocation. The carbon has 6 valence electrons. It would love to share 8. The nucleophile has a lone pair that it can donate, and so in the process we form a carbon nucleophile bond. We have a +1 species of the carbocation reacting with the -1 species of the nucleophile. So this two-step mechanism is what's proposed for the SN1 mechanism, where now the 1 stands for a unimolecular process. Okay? So now what we need to do is we need to justify, well, how do you get the kinetics that you do from a unimolecular reaction? And we have to go back to general chemistry to remember that steps of an elementary steps of a mechanism is what I call them. The elementary steps don't have to occur by the same rate. Some step might be slow, some step might be fast. So simplifying this, we have a first step, which is the alkyl halide breaking the carbon-halogen bond to make the carbocation, and then a second step where the nucleophile adds its pair of electrons to the carbocation to form the product. Now, one of the things that you learn in general chemistry is that when you create elementary steps of a reaction, you can write the rate equation for that elementary step. Not the overall reaction, but for the elementary step. So in this case, the rate of this first elementary step would be the rate constant times the concentration of the alkyl halide to the first power. Because when you're writing the equation of the elementary steps, what you find is that you can use the stoichiometric coefficients. Not the overall reaction, but only in the elementary steps. So then the rate equation of the second elementary step, number 2, would be that the rate would equal rate constant times the concentration of the carbocation times the concentration of the nucleophile. Both of those to the first power. So these rate equations of the elementary steps are what we're going to use to determine which is the fast and which is the slow step. So we remember that the rate equation overall was determined experimentally to be the concentration of the alkyl halide to the first power. Now, when you're looking at multiple elementary steps, the slow step is going to be the step whose rate equation matches up with the rate equation that's determined overall, and this is the overall rate equation. So in this case, since the first step has a rate equation only dependent on the alkyl halide and the overall rate of the reaction only dependent on the alkyl halide, then I would conclude that step number 1 is slow and step number 2 is relatively fast. If the situation was reversed, the nucleophile would show up in the rate equation. When I changed the nucleophile, it would have affected the rate. And so what we have is we have a two-step mechanism here, with step number 1, the formation of the carbocation, being the slow step, and the reaction of the nucleophile with the carbocation being the fast step. Okay? So if you think about the mechanism of this reaction, think about it this way. You know, the carbocation is slowly forming, slowly forming, slowly forming, and then once it forms, boom, the nucleophile adds in the fast step. So what's the overall rate going to depend on? How fast I form the carbocation. So then that's why we get the rate equation to be only the alkyl halide to the first power, because the slow step the slow step only has the alkyl halide as its only molecule in the reaction, so it's unimolecular. Now, this slow step is what is called the rate determining step of the reaction. So the rate determining step of the reaction is the slow step, and in this case it's the formation of the carbocation. That means that this reaction is unimolecular in kinetics, and the key step, the slowest step in the mechanism, is a unimolecular reaction that only involves the reaction of one molecule. Okay, so when people started to determine the kinetics of these substitution reactions, they probably were really surprised that the tertiary didn't have the nucleophile's concentration affect the overall rate. Then that led them to try and figure out what the mechanism is consistent with that rate equation, and this is what they proposed. And this is what it hasn't been disproven yet. My PhD advisor used to say that, when you're trying to prove a mechanism, what you end up doing is just trying to disprove all of the possibilities, and then whatever you're left with is probably correct. But there's always a possibility that new evidence could show up to, break that mechanism. So these mechanisms have all been worked on for probably 100 years. Okay, so this is unimolecular SN1 substitutions. So what this means in terms of the reaction coordinate diagram is this carbocation is now what we would call an intermediate. And I'll go back to the reaction diagram in a minute, or the reactions themselves. But in the reaction diagram, intermediates are basically the valleys in the energy coordinate diagram. Remember, the transition states, and that's the symbol for a transition state. The transition states are the peaks. So we have one transition state before we form the intermediate, and we have a second transition state for the formation of the final product. Okay, so it's like a double hump camel. The valleys then are the intermediates. And there's a definition difference between intermediates and transition states. Intermediates are unstable, and so are transition states. They're both unstable, but an intermediate is less unstable than a transition state. The key is an intermediate, you could study an intermediate. It may be difficult, but you can study it. You sometimes can put it in a bottle and study it using spectroscopic techniques. Transition states cannot be studied directly because they don't exist for a long enough period of time, whereas the intermediate carbocation can be studied. And the heyday of carbocation chemistry was the 60s. Okay, so that's the difference between an intermediate and a transition state. Now, going back to the overall reaction here, an intermediate is something that is produced in one step of the mechanism and then reacts in the second step of the mechanism. So when I add these two reactions up, what do I get? I get alkyl halide plus nucleophile making the substitution product and the leaving group. So intermediates are produced in one step, used as a reactant in another step. Okay, so that's the intermediate, and in this case the intermediate is a carbocation. Now we need to talk a little bit about carbocations and what their stability are, Because what we're going to talk about is, okay, so if I have an SN1 reaction, which alkyl halide is going to react the fastest? Primary, secondary, or tertiary? So let's talk about carbocation stability. So first of all, in terms of carbocations, they have a positive charge. They only have 6 valence electrons. Anything I can do to push the electron density of carbon closer to 8 is going to make this carbocation more stable. The problem is I can't get it to 8, right? Because then it wouldn't have a positive charge. But anything I can do to get it closer to 8 is going to make it more stable. Well, how am I going to do that? What I'm going to do is, what if I attach an alkyl group to that carbocation? Well, that's going to stabilize the carbocation. How? Well, remember that the carbon-hydrogen bond has the hydrogens slightly positive and the carbons slightly negative. Remember that from our discussion about hydrocarbons. Well, this carbon with its slightly negative electron density can now push that into the carbon. And so when you attach an alkyl group to a carbon with a positive charge, it's going to push a little bit of electron density and make that carbon go from 6 valence electrons to maybe 6 point whatever. It's going to get it closer to 7 or 8. Now, where's the threshold? A carbon with 3 hydrogens is going to be very unstable, so unstable that it's not going to form. And I'm going to add in solution. Will it form in a very high energy environment that we'll talk about in Organic 2 lab in mass spectrometry? So, yes, you will not draw the structure of a methyl carbocation, nor will you draw the structure of a primary carbocation. Primary carbocations are too unstable to form in solution. Unfortunately. So one alkyl group is not enough. What about 2 alkyl groups? Two alkyl groups is enough to form a stable carbocation in solution. And so if you have a secondary carbocation, a secondary carbocation will be stable. How about a tertiary carbocation? Well, a tertiary carbocation would be the most stable carbocation because now it's got 3 alkyl groups pushing electron density. So that's going to give you the maximum amount of electron density that you can add to that carbon. So that's going to be more stable. So in terms of forming the carbocations, tertiary carbocations are more stable than secondaries, which are infinitely more stable than primaries, to the point that we don't draw primary carbocations in solution. Okay, so just as kind of a review, the things not to do in organic chemistry. Number 1, don't take it, but you don't have a choice. Number 2, 5 bonds to a carbon. Number 3, primary carbocations. And that's as far as I've gotten through the years. So that is our 3 rules of things not to do in organic. Primary carbocations are too unstable to form. So that's how the stability of carbocations go, because every alkyl group you add pushes more electron density into the carbocation and increases its stability. Okay. So now in terms of stereochemistry, what happens in an SN1 reaction regarding a chiral alkyl halide? In an SN2 reaction in the last lecture, we saw that a chiral molecule in an SN2 reaction underwent inversion of configuration. What happens in an SN1 reaction? Well, in an SN1 reaction, once you break the carbon leaving group bond, you form this carbocation. Now, what is the structure of a carbocation? Well, if you think about that, a carbocation has 3 bonds and therefore would be sp2 hybridized, and so it would have an empty p, or it would have a p orbital, unhybridized. What's in it? Nothing, because the carbon has a positive charge. So the p orbital turns out to be empty. And that's where the nucleophile is going to add its lone pair to form the carbon nucleophile bond. So what we have is we have an unhybridized empty p orbital. So now when you form a carbocation and you're the nucleophile down here, which lobe are you going to add to? Well, you're going to add 50% to each lobe because there's nothing stopping you from adding to either lobe. So you're going to add 50% to the left in this case and 50% to the right. What does that mean for the stereochemistry of this reaction? If I start out with this molecule, which hydrogen's 4, bromines 1, ethyl group is 2, methyl group is 3, clockwise this is the R, what am I going to get? Well, what I'm going to get is the formation of this carbocation. If the nucleophile adds to the left carbon, what happened? Well, I formed 1 enantiomer. If the nucleophile added to the other carbon, what do I get? I get the opposite enantiomer. And so, in this case, I'm going to get a 50-50 mixture of enantiomers. And what is that? A 50-50 mixture of the 2 enantiomers is a racemic mixture. A racemic mixture has a specific rotation of 0 degrees. So when you do an SN1 reaction, you start with an optically active halide. You end up with a non-optically active product because that is a racemic mixture. Okay? And so that's the stereochemistry of an SN1 reaction. So this specific example, if I took the R2-bromobutane like I did with SN2, I lose the bromine. I now have this carbocation, which is going to have the empty p orbital. If my nucleophile now is CN minus attaches to both sides, what do I end up with? I end up with the S enantiomer and the R enantiomer, and since they add 50% to the right, 50% to the left, I end up with a racemic mixture. And so that is how that's the stereochemistry of an SN1 reaction. You end up with a racemic mixture in a non-optically active product. So it might be easy to tell for reactions SN1 or SN2 by just simply reacting a chiral molecule and seeing whether you get a chiral molecule or whether you get a racemic mixture, which would not be chiral. And again, this is how people proved the mechanisms that they were proposing. Okay, so in terms of unimolecular reactions then, SN1 reactions, here's the summary. And we'll get more into this in the next lecture, including talking about solvent effects. But the mechanism involves at least 2 steps. Cleavage of the carbon-halogen bond to form the carbocation, and then attack of the nucleophile on the carbocation to form the nucleophile carbon bond. The reaction is unimolecular. The rates of the two mechanistic steps are different. The formation of the carbocation is the slow step, which is called the rate determining step, and the attack of the nucleophile is much faster. And since the first step is the fastest, the kinetic rate is only dependent on the alkyl halide. It doesn't depend upon the nucleophile concentration or how good that nucleophile is, which we'll talk about in the next lecture. The rate of an SN1 reaction is only dependent on the stability of the carbocation intermediate. And so alkyl halides that form stable carbocations undergo SN1 the fastest, while those that cannot form stable carbocations cannot undergo SN1. So benzylic, allylic, and tertiary and secondary all can undergo SN1. And we'll talk about what these are later on in the semester. But tertiary is faster than secondary. Both of these, since they can form stable carbocations, undergo SN1. Primaries cannot undergo SN1. And this should say no SN1 reactions. But just to end this discussion of SN1 versus SN2, well, what if you had a primary halide? Primary halides can undergo SN2, right? Because they have less steric hindrance. Tertiaries had too much steric hindrance and they couldn't undergo SN2, but guess what? They form the most stable carbocations, so they undergo SN1. The real problem are secondaries that can do either one. And so we have a whole continuum of possible SN1 and SN2 reactions with secondaries. And so what we're going to need to think about is okay, how are we going to classify secondaries into SN1 or SN2? And we'll deal with that issue. First, we're going to oversimplify, and then we'll begin to include more details to sort of get into the gray area. But at the beginning here, we're not going to jump into the gray area because that just becomes too confusing. And so we're just going to kind of make some very black and white rules, some very definitive rules that then we're going to have to muddy up as we go along. Okay? So the last thing is what happens when an optically active alkyl halide undergoes SN1. The product is not optically active because it's a 50-50 racemic mixture. And that's because the two enantiomers result from the attack of the nucleophile on both empty lobes 50-50, and that gives you a racemic mixture. Okay? So that is the beginning of SN1. We will continue this discussion in the next lecture video.